Okay, so continuing on with um, the main concepts for projectile motion. So this is an equation, the range equation that you'll see in your book that you really shouldn't use because you don't have it on your equation sheet for the AP exam, and unless you memorize it, it does you no good. And so, just to save memorizing space, brain space, really it's better to just use the kinematics equations that you're given and get it from there. Um, and I'm going to show you how to do that right now. So the range equation is range equals v initial squared, oops, um, times the sine of 2 theta over g, where r, so if you launch a projectile and the starting height and ending height are the same. For example, if you kicked it on the ground, then r, which is this length, is in this angle. If you have the initial velocity at the very bottom here is v naught at this angle. Notice this is not a component. This is not an x component or y component. This is the actual resultant velocity going that way. Then you can find the range from the initial speed and the angle, which is useful. But we can do it with kinematics. We can get this with kinematics as well. And I know concept 5 is to show you how to set up a separate list of givens for the x and y direction. I think I'll mix 5 and 4 together and show you this column step right now. So when doing projectile motion problems, I would set up x variables, x initial, x final, v initial x, that's a 0, v final x, ax, and t. I don't put an x for t because, as I'm going to discuss, the time is the same in both columns, in both directions. Then over here we got y initial, y final, v initial y, v final y, a, y, and t. And we know that there is no acceleration in the x direction. And we know that gravity, 9.8 meters per second, often called little g, is the acceleration in the y direction. What I'm going to do to get this equation, though, is to actually only use half the range. And why I do that is because I know the speed up here in the y direction is 0, whereas if I just do the whole range, the speed here and the speed here are the same, just in opposite directions for the y speed. And that doesn't help me at all, because I don't get a change in speed. So we'll call this 0 and 0. That's here 0 height and 0 distance. And we'll go r over 2, which is going to take me right to here. And here we'll just call this the height, but we're not going to even use this because it's not in the equation. And then here we know that the x component of the initial velocity is the initial velocity times cosine of the angle, and the y velocity is the initial velocity times the sine of the angle. That's just this little triangle here. This is the y component, and this is the x component of the velocity. And in the y direction, it comes to a stop. Now, well, I'll talk about this after I do the x velocity. So this one's easy because there is no force in the x direction, so it's a constant velocity. So this is the same as the initial. And we'll just call this t, because we don't know the t, how long it takes. So one thing to notice here is I've said that g is positive, meaning down is positive because gravity pulls down. And you might have noticed, well, this initial velocity is up, so why don't you make it negative? But I can do this. Um, hold on a sec. Let me think about this for a sec. Yeah, I can do this if I say that actually up here is 0, the initial y, and down here is h. Then I just do it on the way down, because on the way up and on the way down are like mirror images of each other. They actually, whatever happens on the way up is the same thing that happens on the way down. If the speed right here is 10 up in the y direction, then the speed right here is 10 down. So I can make all these positive as long as I'm doing the downward part of the graph. Okay, so a couple things to notice is in the y direction, I only have, if I want to find the range, well, first off, I want to find the range. That's in the x direction. But for x, really the only equation that works is the following. And this goes away because a is 0. So this equation in the x direction is really just involving these three variables. And as you can see, if I plug them in, r over 2 equals v naught cosine theta t. I don't know if I don't know the initial velocity, and I don't know the angle, or I don't know the range, then I get too many unknowns here. So I'll need a system of equations, or I used to call them simultaneous equations. I'll need another equation in the y direction, and I believe this is also, yeah, this is number 6. So I'm kind of covering 4, 5, and 6 all in one here, which is good. I'll need the y direction, a y direction equation to get rid of a variable here. And what I want to get rid of is actually t, because you see there's no t in here. So over here, the equation I can use is v equals v naught plus at. And again, if we're going on the way down, then I really should have switched these. V initial would be 0, so maybe I'll just draw an arrow here. That's kind of what I was missing when I was thinking about this earlier. Really should switch these so that your initial velocity is 0 if we're going on the way down, and your final velocity is v sine theta. So then what we got here is v initial sine theta equals 0, because again I switched them, so the initial velocity up here is 0 if we're going on the way down, plus gt. G is acceleration due to gravity. If I solve this for t, then I can plug it in here and get rid of t. So let's do that. T is going to be v initial sine theta over g. I just divided by g, both sides. Take that, put it in here, and you get r over 2 equals v naught cosine theta, v naught sine theta over g. It's starting to look a lot like this up here. Simplifying, we'll bring the 2 over to the other side. We got r equals v naught squared, this one times this one, times 2 cosine theta sine theta over g. And we're really there, but there's a trig identity that says that 2 times the cosine theta times the sine theta is equal to sine of 2 theta. So you can just substitute that trig identity in here, and you get the range equation. So, just to summarize, because I think I've covered all three of the following concepts, don't use a range equation, because you can use just regular kinematics equations, and these are the two main ones right here. To get that, that's where the range equation came from, is kinematics equations. You don't have to memorize these, or you will use these so much that you'll probably memorize these, but on the free response, these two are given to you. And so yeah, and then we got that in order to solve projectile motion problems, it's very helpful to set up a separate list of givens for the x direction and the y direction, and the time variable t is the same for both directions. So that's what I did here to start us off, and then you just fill in what you know. This can often be, some of these are easy, like this is always g, this is always 0, but some of these can take a little bit of brain power to figure out exactly what goes in here. Like, how did I decide to do r over 2? Well, it was just experience, because I know that if I do a whole range like this, the initial velocity in the y direction and the initial velocity in the x direction are essentially the same, just in opposite directions, and that doesn't give us any useful information. Also, the height, there isn't a change in height, so there's basically a bunch of zeros here. So it's a very useful location in projectile motion is the maximum height, because we know that y velocity is 0 up there, and so that's why I decided to use this. And finally, use this system of equations for projectile problems where too few givens are available. Usually t is the link between the two equations. Because I did this all in letter form, it was hard to see that we didn't have enough givens, because they were all just variables, so which ones aren't given. But in an actual problem with numbers, it's easier to see that. And so um, this using one equation in the x direction and one equation in the y direction, and using t as the link between the two, will be more obvious when you're actually given numbers. Cool. So that takes us to 2D motion, circular motion, and I'm just gonna take it to the next level. I'm just gonna go to 15 minutes, and the last video is probably gonna be really short, which is cool with me, probably cool with you. So circular motion. So in this case, instead of moving in a parabolic path, we move in a circular path with a center and a radius. And so speed is circumference times time. Speed is really distance over time, but when you're moving in a circle, the distance you travel if you go around one circle is the circumference. And as you know, if this is the radius, then the circumference is 2 pi r. And so the speed, if you're going around a circle, is 2 pi r times the time. If you want the period, which is once around time to go once around, then t really does equal 2 pi r over your velocity, because 2 pi r is one circumference. If you had like 4 pi r, then that's twice the period, because you've gone around twice. Yeah, that's pretty much it for this. But this is useful in lots of problems. And then, so that was the speed. Once you have that speed, which you can use right here in place of, they usually write v, but it really means speed for the most part. In this case, you don't really have a direction here. The direction is always, well, the direction of this velocity is always changing, right? If you're right here and you're going clockwise, then your velocity direction is that way. If you're down here and you're going clockwise, your velocity direction is that way. So it's not as useful to think of velocity because the direction is always changing. But anyway, centripetal acceleration, often written as AC, or A centripetal, is v squared over r. Again, where r is the radius and v is your tangential speed. It's really just how fast you're going. But let's say you're in a car and you're taking a turn around a racetrack. It's just your car speed, what you see on the odometer or speedometer. Yeah, at any moment in time. And you can see if your speed changes, if your speed increases, your acceleration increases. If your radius increases, your acceleration decreases. That means it's easier, in one sense, I should say, in one sense, that's kind of explains why it's easier to go around a bigger circle, because you need less of an acceleration to keep you moving in a circle. that's one tricky thing about centripetal motion, is that you need a force to keep you moving in a circle. But we'll talk about that in the fourth chapter. And with that, I'll end this video and do number 3 next time.